Start. Good morning, good afternoon, everyone, depending on where you are. My name is Julia Matevosyan. I'm a chief engineer at ESIG, and I'm kicking off the second day of generator interconnection workshop, which we are organizing jointly with ESIG, NAGF, NERC, and EPRI. So yesterday we had a very successful 2 sessions focusing on generation interconnection process, and transmission process and needs for integration of these 2 processes. The first session was more general, talking about 2 processes and similarities and interjection between the 2, and then the second session was more deeply going into details and presenting some of the case studies where integration has already been done and showed some benefits. So today we'll focus on interconnection studies and then specifically on modeling. So these will be 2 sessions of the day. I would like to remind you all to use slido.com for your questions, and the code of today is ESIG 10. And so without any further ado, I'll give word to Ryan Quinn from NERC for the first presentation. Ryan, could you briefly introduce yourself as well? Thank you.
Thank you, Julia. Well, while I'm getting control here of the screen, I'll introduce myself. My name is Ryan Quint. I'm Director of Engineering and Security Integration here at NERC. For those that are in the renewable space, you're hopefully familiar with the number of the activities we have underway, including the Inverter-Based Resource Performance Subcommittee, as well as all the disturbance reports, alerts, lessons learned, etc. We've put out over the past 6-7 years now. So wanted to just share some opening remarks. Many of the points I'm going to cover here are going to be touched on in more depth by the 2 panels we have this afternoon. But obviously NERC has a big vested interest in ensuring reliable operation of the bulk power system. And some of the key findings that we've identified is really that a lot of the root challenges or issues, reliability issues we've identified over the years across multiple resource types really comes down to the interconnection process. And I'll touch on some of that here briefly. So for those that are maybe new to this space or unfamiliar, we're essentially calling it a saga because a saga has a hero, and the hero is, I think, industry taking action to address these issues. So this goes all the way back to the Blue Cup fire that we had in 2016, and we published a number of disturbance reports. They started off as events in California, and you noticed they were getting more common, more frequent, and larger in magnitude. And then all of a sudden we had the Odessa disturbance last year, a big event in Texas, a number of facilities affected, and those facilities were large bulk power system facilities and relatively brand new, right? So it raised some alarms for us. We then had 4 events in California in 2021. And just this morning, we published the Texas Panhandle wind event. So if you haven't seen that, there's a new disturbance report out there now talking about many wind plants anomalously behaving or abnormally tripping or reducing power output for, again, a normally cleared fault in the Texas Panhandle area. We, of course, have the extremely large Category 3, what we're calling Odessa 2, that happened a couple months ago. Where that was a combination of many solar plants reducing power output, tripping, etc., in conjunction with a lot of synchronous generation lost at the same time. That event was on the order of magnitude of 2,500 megawatt loss, encroaching very close to ERCOT's largest single credible contingency size, right? What we plan and design the system to be able to withstand. So again, these events are getting larger, more frequent, and more concerning, frankly. It definitely has elevated the inverter risk issue topic to very near the top, if not the top risk issue right now, in addition to cybersecurity. In the past couple disturbance reports, we've highlighted this 3-pronged approach, and we're working very hard to put this approach into motion. And the topic here today with the NOPR is a big step for item number 2. We highlight we need industry to act now, adopt the guidance that has been put out. There's a number of materials out there in terms of educational content, reliability guidelines, white papers, technical reports, etc. the industry can learn from and take action on. But number 2 is really something we've been strongly advocating now for a while, is that we need to modernize and enhance the the FERC generator interconnection procedures and agreements, really focusing in on ensuring we have the correct models to run accurate simulations and make sure that everything gets trued up during the trial operation and commissioning processes, as well as figuring out how we adopt 2800 appropriately. And last there, we have a significant amount of standards projects underway regarding the NERC reliability standards to address many of these issues, both performance-based modeling studies, etc. We're rolling out a kind of a formalized strategy that we're taking to address the inverter risk issue. Really, there's 4 pillars. The first pillar there being risk analysis, doing the deep root cause analysis of events, publishing the disturbance reports with strong findings and recommendations, issuing alerts where necessary, and providing as much lessons learned as we can. And hopefully we'll be quite a bit more agile to get technical content out quicker on a number of the very kind of detailed engineering related issues that we're identifying, so the industry can take action on those more effectively. The second pillar there is the interconnection process improvements, improving the GIA, the GIP, enhancing local interconnection requirements, making sure we get good models and correct studies, and again, adopting 2800. The third column there is really pushing out best practices and education through these types of co-sponsored workshops, outreach, engagement, publishing reliability guidelines. And then obviously, being NERC, our fourth arm there is the regulatory enhancements, driving improvements to NERC reliability standards, reviewing and maybe modifying the bulk electric system definition, introducing the concept of inverter-specific requirements and standards where appropriate, and then enhancing our risk-based compliance approaches for relevant standards of interest or of risk. There's a lot of content out there, like I mentioned, so hopefully folks are familiar with this. If not, my contact information is at the end, and you can feel free to reach out to me anytime. One thing related to the topic of discussion here today is the modeling issues, right? NERC has published a number of technical reports and documents. We've included modeling analysis in our disturbance reports, and we feel fairly comfortable in saying that the vast majority of models out there are either incorrectly parameterized, inaccurate, or unable to represent the vast majority of causes of abnormal performance and tripping that we've seen in all of the disturbance reports that we've published, right? These are some example plots from the different reports, the disturbance reports we put out. The bottom down there, the reality versus model, that's coming straight out of the wind report that was published this morning. You see the vast differences. It's not do my squiggles match and do I want to get into a technical debate on squiggle matches, right? There are vast discrepancies between what we expect the plants to do and what the model actually shows that they did, right? What actually happened out there, right? So we need to get those types of issues shored up, and that needs to happen during the interconnection process so we don't find ourselves operating in an unknown, unexpected operating state. So just to touch on some of the key points of the NOPR itself, I sort of highlighted the relevant portions of the NOPR. Obviously, it's a very extensive, long NOPR, and you need to read it in its entirety, but tried to reflect on some of the points that NERC has highlighted over the last few years related to what's in the NOPR, and obviously we'll be providing formal comments to the NOPR overall. So the first thing I wanted to highlight, right, the NOPR is covering really 3 things. We need a validated user-defined RMS positive sequence dynamic model. We need an appropriate parameterized generic, I don't like the term generic, I'll call it standard library positive sequence model, including the block diagrams, the control settings, etc., that correspond to a list of acceptable models. And then third, we need a validated EMT model if the transmission provider will need to run EMT studies. On the NERC side, we've essentially said there's a very strong likelihood that we will need EMT studies for newly interconnecting plants. As we move forward into an inverter-dominated system, it's important that we get those models now and not try to get them later after the plant has gone through multiple ownerships and the OEM is no longer in business. We've run into these issues in the past around the world, and we can learn from that. Right, so things to highlight here, all of these models play a purpose, right? The full suite of accurate models is critical to conducting sufficient amounts of reliability studies. Each model fills a niche or plays in a unique role in the different types of studies that are conducted. right? The user-defined model is important because it needs to reflect actual installed, planned equipment control settings, modes of operation, and protections that are going to be put into service, right? Running studies using models that don't match reality or planned reality are as good as useless, right? There is no point to run a study with a model of fake parameters or genericized parameters, because that's not what's going to be installed. And that's what we find when we go in and we do root cause analysis. The vast majority of those models fall into that bucket. They don't reflect reality at all, right? So there's obviously something falling apart in the interconnection process where that is not being trued up, and we're running studies of equipment that the model does not match reality, and we need to fix that. The standard library models, they play an important role in running interconnection-wide studies. They're maybe not quite as accurate, but they're trustworthy. They're good in the interconnection-wide base cases, and they allow us to get an understanding of large-scale, wide area reliability issues that we may be facing, so long as, again, they're accurately and adequately parameterized with appropriate plant-specific settings. When I see the term generic in any document now, it scares me, because industry assumes that means I can use generic parameters. I can pull the generic models out of the simulation documentation, which is not necessary. So I appreciate that the NOPR highlights we need appropriately parameterized models, which I'm going to call standard library models, right? All of these things, like I mentioned, get us to a point where we can run sufficient studies that are accurate, which is critical for making reliability decisions. And I'll highlight it again, right? Inaccurate models lead to inaccurate studies, which lead to poor interconnection decision making and unreliable operation. And we've seen that with the existing fleet. We need to fix these issues, right? Again, those models need to include the controls, the modes of operation, the settings, the protections, the system, the plant configuration, etc. We need to get all of that stuff right so that we can know if that plant has the ability and capability to meet its requirements, its interconnection requirements, the ability to ride through expected disturbances on the grid, and to provide essential reliability services. Last thing I'll mention here is, obviously this is extremely complex as you work through the interconnection process. We heard yesterday the large developer said every project is entirely speculative when you put it in the queue, right? Equipment is maybe not selected at the time of the interconnection request, but that's what creates this overinflated large interconnection queue, where both sides, the development side and the transmission side, are saying I have an unmanageable, untenable queue that is full of 90% speculative projects, because I need to know certain information before I move forward. The introduction of the first ready approach can hopefully help us there to some degree, but it's important to recognize that we need to make sure that accurate modeling information is provided at the time of interconnection, which can enable and allow proposed modifications throughout the interconnection process. But there needs to be very clear procedures in place to ensure that those changes or modifications then result in updated models and restudies of the facility to ensure reliable operation. And we all need to acknowledge that when we conduct restudies, that will slow down the process, but it is an essential part of reliable operation of the grid that we can't overlook, right? So we need to figure out a reasonable approach to that issue, because as we know, as we hear, all of these restudies drastically lengthen the queue time, right? The timeline to interconnection, right? So to the extent we can minimize restudy, we can know information as early as possible, the less speculative the projects can be, and the more accurate, reliable the studies will be. So that's all I've got to kind of get us kicked off. I hope that was helpful to kind of set the stage, and I know the presenters moving forward will go into much more detail there. I don't believe we're taking questions at this time, but I put my contact information there. If anyone has any questions, feel free to reach out to me. And if you're interested in getting involved in some of the NERC technical committees, again, feel free to reach out to me. So I think with that, I'll hand it over to Roberto Favela to kind of start facilitating the first session there. Thank you.
Hi, everybody. My name is Roberto Favela, and I'm the manager for system interconnections for El Paso Electric. I've been in this business, the interconnection business, since 1999, and I'm going to just highlight what Ryan just said, which is the interconnection studies are the most important part and are taking the most relevant nowadays than ever before due to the risk that the new interconnections are posing to the system. So highlighting that interconnection and having accurate modeling and doing the right studies and the quality of the studies being good, it's of utmost importance. Today we're going to be having a panel of four panelists that are going to be talking about the interconnection studies. It's going to be Divya Hutakovi and from Orsted, Mario Hayden from NL Green Power, Alex Shatuk from Vestas, and Jens Boomer from EPRI. With no further ado, if you have any questions, please use them in Slido, and please take it away, Diva.
Diva, you're on mute.
Oh, sorry. Thank you, Roberto, and thank you, Ryan, for that great introduction to start the day. I think one of the things I would want to start off is give a little bit of background on what Orsted does. And we'll go more into the process, interconnection process, and look at it only from a modeling perspective. The interconnection process from a project development perspective is a lot more than just models. And I'll just walk you through some of the timelines we see in a typical offshore wind project development. Before I get into this, when does offshore wind farm design start? Just a little background about myself and the company. Orsted, we are offshore wind developers. We have over 30 years of experience building offshore wind in Europe, and we have about 5 gigawatts of offshore wind in various stages of planning, design, and construction in the US. These are projects that are awarded by the state, and we would be getting them online somewhere before the turn of this decade. And at Offshore, my main role was managing grid connection. I was focused mostly on the Mid-Atlantic region, where we have a number of offshore wind farms coming up. And again, I've been through the interconnection process, looking at it from an offshore wind perspective. And US, we do see that there is a lot that we are learning in terms of US region-specific processes. This presentation is going to be focused on really the US region, and we're not going to look at Europe. And also, again, as I said, I'm going to focus completely on the fact that we have sorted out the interconnection costs, and we park that aside, and we are looking only from a design perspective. So let's get started on really, when does offshore wind farm design start? So this is really the first step in our design process. We go through what is known as Bureau of Ocean Energy Management, and we get the ocean lease. Obviously, we have to get to that. But before that, there are some reviews and surveys that are done, and they are published by Bureau of Ocean Energy Management. And our time, the development starts when the lease is granted. This is only the ocean lease, right? And post that, we start doing surveys in the ocean, and we start building our design. And at this point, when we submit, we have a preliminary idea about turbines and some idea about how much of capacity we are going to plant in there. But we don't have a lot of details. So we start more detailed site assessment and surveys. This includes the ocean survey. What are the options for our onshore POIs? What are the different cable routes we can get from the ocean to onshore? So there's lots of investigations done. And from a timeline perspective, we do not submit an interconnection request at the start of site assessment and surveys because we don't have a lot of information. More towards the end, we submit an interconnection request to the independent system operator in the United States. And we try to do it generally before we submit the detailed construction and operation plan, which is known as COP. And there is a rationale why we do that. Let me just go over to that. Because one of the things that this federal offshore wind process does is they impact our designs. They decide based on environmental reviews of where exactly we could go in and what kind of equipment we can put in the ocean, what kind of equipment we could put onshore. It's a lot more than just the impact on animals and protected species, and it also looks at visual impacts, noise impacts. So there are lots of reviews that go on. Let me move to the next slide. From a planning and design perspective, we are always iterating. Some of the initial assumptions we made on the grid and the assumptions we made on the turbine technology available. Now, a lot of these turbines that we have may not be already available. These are not off-the-shelf turbines. So they're still under development, but we have a good understanding with the OEM, and we have decided to go in with that platform, but we may not know the exact controls. We don't have a good idea about the rating at this point. We start our federal and state permitting process, which is basically we start the BOEM process or the NEPA process, that is the environmental reviews based on some of the assumptions we made in terms of technology and the grid models. Towards the end of the permitting, we start the interconnection process before we finalize a construction and operation plan. We start the interconnection process. And really the reason we do that is because of the iterative nature. So anything that changes around the grid model would impact our designs, and that in turn would have an impact, a cascading impact on our permits. So we may not have covered that in our permits. And whenever we go into this federal permitting process, we are giving a design envelope. So it's really broad. There are many options that Bureau of Ocean Energy Management and the subsidiaries thereof can pick from these big envelope that we provide. And this whole process from planning, design, and construction takes about 6 to 8 years. If you look at, again, the relationship between the federal permitting and interconnection process, once we make any changes to our design, it could be as simple as rerouting our cable. Then there are engineering implications because these are high voltage AC cables. They're all at transmission voltages. And there's reactive power compensation that would change. So it alters the design. And that potentially necessitates some reviews from the ISO or the Regional Transmission Organization. And any inputs we get from there, if we see a negative impact on the system performance and we may alter our design, then we have to go through the NEPA process again if that's not included in our design envelope. And I'll walk you through an example on how this has been working. So basically, it's an iteration between our design changes and iteration between the NEPA process and the RTO or ISO interconnection process here in the US. Just to look at the interplay between interconnection process, the design, and the federal process, I've just made a high-level kind of a block diagram, I would say. So input of one process impacts our design, and changes to the design affects the other process. So this iteration goes on for quite a significant amount of time. Now, there's a little bit of, I think there was an animation, if doesn't seem to be playing here. So let me
Yeah, you would have to share your screen for the animation, Divya. Sorry about that.
Yeah, no problem. I can share my screen.
5 minutes left.
Yep. I should be able to wrap this up quickly. Can you see my screen now?
No, not yet.
No? Can everybody see my screen now?
No, just your presentation. We're not able to see the video.
Oh, I think yeah, I think one of the things
Divya, do you want to leave this for the Q&A meantime?
yes, that would be helpful. I think let me not do the screen sharing. We'll go back. Sorry about that. We'll just go back to the WebEx. So just to set the stage up with an example, let me quickly run it. This is an actual offshore wind farm design that we were doing, and this is something that we did experience. So as I said, we give an envelope on the cable route, and it's unknown. So the federal NEPA process would tell us exactly what this route is going to be. And in some cases, we have seen that the cable length estimates is beyond a worst case assumption. And why does it even matter? So if when we exceed some limits, obviously we need reactive power compensation. And once we add reactive power compensation, the impact to the grid might be very different. And given that the cable route has increased significantly, there are engineering challenges, and I'll get to that in the next slide. It might also decrease the short circuit strength at the turbine terminals here in the ocean. And in some project, we had to get synchronous condenser back in. And again, at that point, we are restarting the federal permitting process. And the NEPA process, the permits can change a lot of things in our design, including the number of turbines, the layout, cable routes, where we locate our reactive power compensation or supplementary devices. Everything is up in the air. From a design perspective, just going by the engineering, I think the grid support device that we would need would be very different. And most often, to mitigate any of the issues we are seeing in terms of meeting the grid requirements or the TO requirements, we often use grid support device just because of the distance we are electrically from the ocean. We have multiple transformer stages, export cables, and it's very hard to control the reactive power flows. And sometimes the short circuit could be a challenge. So we put in a lot of equipment on our onshore substation. And any changes to the design anywhere in this is going to trigger new federal permits and restudying the ISO process. And this actually brings us to the challenges in obtaining project-specific models from the equipment vendor. Moving on, so I think Orsted and we have a lot of engineers who put in a lot of work, and we work with OEMs because none of these, as I said, is off the shelf. So the turbines are not off the shelf. The transmission equipment is not off the shelf. We customize it and we build it for each project. But because we actually make assumptions on grid model or data, assumptions about short circuit, assumptions about harmonics, we have to iterate. And if we have this information early on, we minimize suboptimal designs and the number of iterations. Also, one of the things we really liked about having a common uniform standard like IEEE 2800 is we know that upfront. It's easier to design it upfront when we start the process. It's very hard to make design changes towards the end of the process. And just a few other thoughts. Again, if you're modeling offshore wind farm, it's super important to model the transmission system because that plays a huge part in the stability. And one of the things we really would appreciate if we could consider is the regulatory process and the interconnection process, the federal regulatory process, the permitting especially, and the interconnection process, if they could be some coordination, that would help us out. And it could reduce the development cycle time, and I think it could also eliminate suboptimal designs. With that, I would say I would thank everyone for hearing this out, and I would stop my presentation.
Thank you, Vidya. Mario, you're up next.
Everybody, you can hear me?
Yes.
Yeah, we can hear you, Mario.
Just share my presentation. You able to see it?
Yes.
Awesome. So thank you, Roberto, for the introduction. Thank you, everyone, for joining. My name is Mario Hayden. I am a Senior Manager of Transmission here at Enel Green Power. And today I'll be presenting on the ERCOT generation interconnection process, which I've had the pleasure of navigating both in my former roles at ERCOT and now at Enel, which is a large developer that builds, owns, and operates renewable energy in North America. So today I'll briefly be talking about FERC's Interconnection NOPR concerning modeling and performance requirements for non-synchronous generators and ERCOT's current practices related to this NOPR. Then I'll dive down into the typical timeline of a large generator that wants to interconnect into the ERCOT grid. Run through individual studies, how each entity that's involved in those studies contributes to those study processes, and how that then leads into the quality stability assessment or the QSA. Finally, I'll conclude by discussing how those requirements in the interconnection process have improved since the inception of the QSA, and then the challenges that still exist as we continue to push for more reliable integration of inverter-based resources in the ERCOT grid. So first, to kick off, I'll give a little bit of context. So as Ryan mentioned in his presentation about the FERC NOPR, specifically the section regarding modeling and performance requirements for non-synchronous generated facilities, which the duration of this presentation I'll probably refer to as inverter-based resources. It's a little simpler to say. So one of the things that they propose is that generator owners provide accurate and validated user-defined models, generic WEC-approved models, and ENT models as needed, depending on if the TO performs ENT studies as a part of the interconnection process. And then secondly, regarding to the rise-through requirements, continue to inject current during the no-trip zone based off of the NERC requirements. The topic that will be covered the most for this presentation is the first regarding modeling. The second will probably be covered much more in depth in future presentations throughout this webinar. So for the ERCOT piece of this, ERCOT has implemented several requirements to enforce generator model fidelity since at least 2017, if not earlier, that basically makes sure that the models that are being submitted not only are accurate in the sense of they are parameterized in a way that doesn't create issues in studies, but also that the parameters are able to be matched to things that can be installed in the field. And then secondly, kind of to that ride-through piece, ERCOT does have requirements currently for ride-through, which have been discussed at length in the IBRTF or the Inverter-Based Resource Task Force, which again won't be the main topic of this conversation. So just giving a little rundown of the typical timeline in ERCOT. So this assumes a simultaneous FIS request and a typical one inverter or wind turbine change, which typically is driven by procurement not being solidified early in the process. I'll also be focusing mainly on the large generator process, since that's going to include the most amount of requirements and be fed into the quality stability assessment. So usually in ERCOT, these processes take about 3 years, which by a pretty large margin is the fastest in the country. And that is despite the fact that ERCOT has some of the most strict modeling requirements in the country. So even if you had a project that you're switching the inverters because you finalized based on procurement, you're still looking at a 3-year timeline, and the most critical path in this timeline is sort of this gray piece, which is the engineering, procurement, and construction handled by the transportation service provider. So even if you're sort of compressing these timelines to make sure you're selecting equipment as early as possible, you're still dealing with the fact that the POI needs to be made ready in order for you to interconnect. So dive into the sort of the first study that's performed as a part of the interconnection process is the screening study. This is a high-level FCITC, which goes through, based off of the point of interconnection that is selected by the generator and the commercial operations date, an idea of what the steady state ingestion capacity is at that point of interconnection. There are no sort of generator specific models required at this stage. Really, what you're providing is the size, the fuel type, the location, and when it wants to be connected. The most important output of this study is that ERCOT will perform at a minimum a topology screening of the POI to determine if an SSR study is required. And based off of that study, or based off of that determination, will determine whether there'll be an SSR study within the process, which could lengthen the process or at risk to the ability of the project to synchronize. Beyond the SSR determination, there's limited value for the screening study, which leads us to sort of the bulk of the interconnection process, which is the full interconnection studies, or the FIS. So the FIS consists of steady state, short circuit, stability, and facility studies, which is pretty common across the country. The naming may be different, but the content of the studies are pretty uniform. The FIS application requires a more detailed suite of inputs, including a detailed and equivalent plant model with a valid collector system connectivity in order to be approved to move on to a kickoff call, steady state study, and beyond. The stability study additionally requires a plant level positive sequence dynamic model package, which includes a model quality test, which I'll dive into in more detail later. And then the facility study, of course, is what is instructing the EPC scope of the TSP in terms of what they're designing, what they're procuring, long lead items, as well as the construction scope, so that there's an actual physical facility for the generator to connect to. So the reactive power study, this is actually a study that is required by ERCOT that says that the generator must provide this study. So usually most generators will use consultants, or if they have the in-house expertise to perform it, they will perform this study based off of the ERCOT recommendations and requirements. Very high level, the reactive power study requires that you're able to meet your voltage support service at a minimum of 35 degrees Celsius. And it also addresses whether your project will have the dynamic reactor capability in order to be connected, and whether it's deficient before losses. In addition, it'll also give a more broad idea of your reactor capability, with which allows you to use shunt devices to make up for losses up to the POI. More recently, the reactive power study has been given more detail in that the co-located resources that are attempting to connect into the grid are now required to be assessed not only as standalone resources. So for instance, if you have a solar and a battery or wind and a battery, addressing the wind and the battery as individuals, but also looking at the resources being injected together just in case losses create need for additional reactor support. Moving down to the SSR study, or sub-acreage residence study. So as I mentioned earlier, this study, the determination of whether this study is required comes from the screening study. If so, the TSP will perform this study and the ERCOT will approve it based off of what the TSP has performed. So all inverter-based resources in ERCOT are required to provide a PSCAD model package, regardless of whether SSR study is required. And this package requires a model quality test, as well as a unit model validation report, which is a hardware-specific report that looks into each inverter's performance in comparison to the model that's being presented in PSCAD. So the SSR studies typically require a lot of coordination between the generator and the TSP, as well as the OEMs, to make sure that there's tight coordination and that the models don't create issues with the study. And if so, that those can be rectified quickly. And where applicable, an ERCOT approved SSR study is required before the product is able to synchronize. This all leads into one of the largest milestones within the interconnection process, which is the correlated stability assessment. So this study is a cluster study that goes over the stability issues that we would see in the grid. What is constituting the study areas that are in the QSA are individual stability studies from generators trying to interconnect within a given time frame that show unstable scenarios. And so with those unstable scenarios, as well as with areas that already have known instability, ERCOT will define study areas to be assessed in the correlated stability assessment, which then leads into their development and or improvement of how their generic transmission constraints, or GTCs, are defined. And sort of, I put a link here that constitutes the white paper that ERCOT published in July 2020, describing GTCs in greater detail. Here's just a table that just kind of gives an idea of the deadlines for the QSA. Basically, if you supply all of your inputs for the QSA by a given date, that dictates when in a given year, based off of a quarter, when you're able to synchronize with the grid. So moving down into a more narrow focus about the QSA, but also just studies in general and how the models have been, the model requirements have been improved in ERCOT since the QSA was formed. So two planning guide revision requests I want to dive into are 75 and 85. 75, very high level, that created the need for model quality tests as a requirement for your positive sequence studies or positive sequence models for PSSE. And then for the dynamic model template, so it basically made sure that there was a more standardized formatting for dynamic models, and it also allowed TSPs to run VRT assessments prior to stability studies in a more efficient manner, and be able to communicate any issues so that the OEMs and developers can fix any issues they're seeing. 85 sort of built upon the spirit of 75, in that it applied those same criteria to PSCAD models. As well as mentioned earlier, introduced the unit model validation, which is on an individual basis, comparing the actual inverter or turbine hardware to the actual model that's being supplied. And then finally, the parameter verification, which is for more of an operational time frame to make sure that the models that are being supplied match to what is actually in the field.
2 minutes, Mario.
Thanks, Roberto. So just really quickly, these two diagrams showing the way the UNVs work, as well as the model verification, which you can pull from the slides after presentation. This is a table that kind of gives a more detailed view of each of the requirements, who's responsible for the requirements, what tests are run, and when the requirements are needed. Quick rundown, some notable other improvements have been made. One, adding the need for repowers to go through the QSA to make sure that there's sort of a closed loop in terms of any changes being captured within the QSA. Secondly, reducing sort of waiting times for the SSR so that now projects don't have to wait 90 days before synchronizing after an SSR study is approved. Adding self-limiting resources, which again sort of adds more nuance to the way studies are performed. And then the last one, sort of clarifying the language in Figure 75 to make sure that the requirements are only needed prior to when a study using the models come together. So moving forward, as sort of my concluding slide, we're still working to make sure that there's study scope improvements related to co-located resources. Also making sure that PSSC and PSCAD models are being aligned earlier in the interconnection process to create or to reduce the amount of issues we see later in the process. Continue alignment with the OEMs and other stakeholders for ride-through requirements and model requirements. And an item that was mentioned earlier that I think is very important is where the NOPR sort of signifies that UDMs, generic models, and EMT models are to be provided. I think there's a need for more clarity about when in the LGIP that these would be mandatory. As mentioned earlier, in ERCOT, the timing of these model requirements align very closer to when the models will actually be used. And there's not a requirement to supply both UDMs and generic models for the same plant. I would also add that because the interconnection agreement is, in a lot of times, the most critical path to interconnection, that it needs to be understood, what are the impacts of having to supply the detailed models in delaying interconnection, and how can we sort of work with FERC and the RTOs and any other bodies to make sure that there's a sort of a compromise in the way that works. So in the meantime, while all the rule proposals are being made and technical discussions are going on in the industry, ANEL has been using ERCOT's sort of way of doing or validating models to sort of inform the way we develop in other regions. With that, thank you for your time, and I'll yield the floor.
Thank you, Mario. Alex, you're up next.
You. I think Julia's going to pull up my slides here.
Yeah, I'm on it. Give me a second. There you go. Right, should be on.
I don't see them yet.
Let me try them. Oh yeah, I haven't pressed share. That would help.
Alrighty, so thank you, everyone. What I'm presenting today is, kind of what happens if, perhaps not everything goes right in the interconnection study process, or, some things are happening just post-interconnection process that need to get mitigated. Maybe something was missed through the process, or, something unforeseen for any number of reasons. But what I want to do before I get started here is the bulk of this presentation here is going to be Vestas specific steps in process. But what I want to make note of is that everyone, all the other OEMs, if you're using detailed user-written models and you're doing proper study process, and you have the capability of moving parameters from the model space into your product, and vice versa, either directly or with mapping, you could do the same thing. It just takes a little bit of effort and a lot of bit of collaboration, both with us and the regional entities and the customers. Definitely, the customers have to be on board with the extra work and timeline and things like that. But with that, let's get started here and go to the next slide. So, what was the main problem? A lot of this is going to be vague and high level because I'm trying to keep all the project specific information, ISO specific information, redacted and confidential. But essentially, what happened was, this project had made it through the interconnection process. It signed its OGIA. It was constructed, and as they were doing some last minute studies, they were noticing some stability issues, some stability constraints due to, I think, two worst case contingencies here. What was happening was, because the SCR at the grid was, 1.75 or lower, depending on the contingency. Basically, what was happening after a fault or a N-1/-1 double fault, they were seeing, nearly 20% voltage swings at the POI, which was essentially just causing the voltage rise through modes to just retrigger over and over again, and basically just swinging the voltage at the POI by 20% every few seconds, pretty much forever. So obviously that wasn't a desired response from the utility, from the ISO. So usually when this happens, the first thing that gets suggested is, we got to do some transmission upgrades. And the reason for that is, a lot of the times, either a generic model gets used where, you might not be able to actually put those solutions back into the product, or, there's not as much, the OEMs don't usually maybe jump into the situation and try to provide solutions. So, usually at this point, kind of the model is taken as is, the plant stability model is, and the performance is taken as is. So what gets suggested is, maybe we'll do some transmission level fixes. So what that can do really is it can kind of add some bloat to the transmission system. It might not be as efficiently used, and honestly, it costs a lot more money to do these solutions below that were suggested than it does to implement controls-based solutions. But for this specific site, due to the low SCR, there's a couple of solutions. There's a substation reconfiguration, so moving breakers around, basically just adjusting the planning contingencies such that they weren't as severe, or such that they would maybe trip the plant offline during the fault instead of leaving it online and causing the stability issue. So the top solution was kind of like a let's change the contingency, let's change the grid so that these problems aren't actually happening. Another solution was a new 138 kV line, which would obviously, what we saw here was partly weak grid and partly transmission stability constrained transmission limit being hit. So the 138 line was more another path for the megawatts and megavars to get out of that pocket. And then a grid side SPC and STATCOM or synchronous condenser, again to help with the SYNCOM could help with the SCR. STATCOMs and SPCs would help push more VARs over that line and get it out. And then the worst case, which obviously no generator owner wants to see, is project curtailment. So basically what that would mean is for any prior outage, any first level contingency that would result in the N-1/-1 that cause these two or cause the adverse response, basically we're going to curtail you significantly, and those prior outages could happen a lot. So basically what it would be is you've just went through the process, you've just interconnected your plant, and now the ISO says, well, you can't put all those megawatts on the grid, you're going to have to operate at a curtailed amount, which would be a pretty terrible business case for any generator owner. So next slide, please. So these are the plots that we got. This is from PSSC. So we started this study in PSSC because this is what the ISO's consultant who was running the studies was using. What we see here is what they were closing out talking about, and you can see the top plots for both of these. It's 20% voltage just swinging over and over again, and you'll see that the reactive power and the power is also just ramping up and down. So you don't want to see this on the grid. You don't want to see 20% voltage swings. You certainly don't want to see 100 megawatts swinging back and forth repeatedly. So this is what we saw at first. Let's go to the next slide. And basically, we got these plots. We saw the results. We got the situation, kind of the whole thing, all in front of us. And basically, what we need to do is, the first thing we need to do is work with the customer, because the customer comes to us and says, can you help us out? We have they're suggesting a bunch of transition upgrades and a lot of money and a lot of time at a potential curtailment. And at this point, the plant was actually curtailed, basically until we got a solution. So there was a little bit of urgency here, obviously, such that we could get a solution before, to get them back, getting the megawatts on the grid and not making money for the plant. So we had a meeting with the customer to kind of explain them the situation, kind of lay out our plan, kind of hopefully give them a decent timeline, which this one took a little while, but we worked as hard as we could on it, and basically prep them for what's going to happen next. And the next thing was, we really got to work with the regional entity and their consultant. We've got to kind of make them understand the problems, kind of make them understand what we were trying to do to fix it. And this was a lot of detailed collaboration between us and the study process, even with their planning study process. So the big thing here, the really big thing was at a SDR of 1.75 or lower, we didn't really want to trust PSSC, the RMS simulation tool for simulations of this SDR level. And throughout the process here, we actually did see at this SDR, differences between the RMS and the EMT solution, just purely because of the nature of RMS solutions and calculating frequency at low SDRs and things like that. So the big thing we needed to do was provide technical justification to the ISO and let them know, hey, we want to do this in the EMT domain. If you want us to do a real study, if you want us to make it as real as we can, we need to do it in the EMT. And then we'll compromise, and say, hey, since your process for the planning process is RMS based, we'll do a solution in EMT. We'll just one-to-one map those parameters over to the RMS model at the end, and then we'll give it back to you, and you can run your full, NERC TPL study on that, and confirm that, we didn't make any other contingencies worse, and that you're running it in the RMS domain. So, the last part of that was, necessary NDAs and data handling and things like that. So what we can't have, since we're an OEM, is we can't obviously see, and we don't want to see any of the other OEM's equipment and machines or anything like that. So we went through the NDA process and got kind of a, a small regional case. The other, I guess it's listed down below, but the other non-Vestas generators were netted out. They were just voltage sources, current sources in the model. And we used that kind of regional model to benchmark the plant response to kind of oscillation we saw on the previous slide against what we were seeing in EMS and in the RMS tool. And then our starting point for the Vestas model was we just logged on to the power plant controller. The Vestas power plant controller and turbine are, one-to-one mapping between each other. So, we can literally just go and download the parameters from the power plant controller and the turbine, put them one-to-one into the RMS model, transfer those back and forth between RMS and EMT, and then put them back into the product at the end, after we, analyze them and things like that. So the next slide. We had all the groundwork laid. We had our model. We had our, kind of regional EMT grid network. So there was 2 worst case planning events, and due to the computational workload that is EMT domain and a larger region, we chose just 2 contingencies to study and analyze. And then the RMS confirmation from the ISO is going to be for the rest of the contingency deck. The however many hundred they have for tens they have for the dynamic studies. So what we had to do really to solve it was this was a little bit complicated. It wasn't just a weak grid. It was both a weak grid and also like a transfer limit. We couldn't pushing all the generation from this generator pocket over the one outlet was just causing the voltage to collapse. So we needed to come up with a control scheme such that we could make the voltage or keep the voltage high enough to get the power out and do this every time without making other contingencies worse. Another thing was that this was actually next door on the same substation as another Vestas plant. So we actually, since we're the OEMs of both and we can coordinate with ourselves, we basically had to coordinate these 2 plants and ensure that we're going to have controller interactions and they weren't going to need, once this got implemented into the field, that they weren't going to, fight each other and make the problem worse. This is something that will be difficult or would be difficult if, the neighboring plant wasn't a Vestas plant, just due to, confidentiality and, working between owners and OEMs and things like that. So that was one lucky thing that we were able to do because it was a Vestas plant. We could coordinate nearby plants, but I would say regional coordination might be important to do these things in the future. So just something to keep in mind when doing these types of studies. So basically what we did was, we got a solution in the EMT. Both those contingencies look good. They'll be on the next slide. And then we took all those parameters from the EMT and just put them directly into the RMS models. Oh, you can go back, sorry.
4 minutes.
Yep, right into the RMS model. So, and that was used to validate the rest of the procedure. And then now we can go to the next one, sorry. So these are the PS scatter, or so the EMT plots. You know, there is some oscillation just due to the one of these plants had you know, doubly fed turbines. So we do see some power oscillations just briefly, but you know, these are within the ISO's criteria. It provides stable response, and you can see the bottom plots. Both of those plants are going directly back to their max power at the end. So last slide. So the conclusions here, there's a long conclusion, but I just want them to be sent out. So, you know, we did a lot of changes to the product, and what we had to do was make sure that all the changes we made, you know, weren't going to basically blow up the converter. We had to make sure that, you know, we did a load assessment internally and made sure that they were going to be, you know, don't affect the lifespan of the product at all. So, you know, well, I mentioned it previously, but, you know, you're going to have to really, to do these things in the future and really kind of make the grid more efficient, there's going to be regional coordination, maybe to come up with non-transmission based solutions. And this will help optimize the BES and BPS. It'll, you know, it could reduce ratepayer costs because you're building less erroneous transmission. And it'll really help us utilize those settings that are in currently and not used in IBRs across the grid, just because, you know, without using, you know, user-written models widespread, you know, you're just using generic models that may not have any of these features. None of the features that we tested and tuned are available in the web generic model. So really, by not using user-written models widespread, we're kind of not utilizing a vast portion of all the controls and features that are out there at this time. So thanks.
Thanks, Alex. Jens, you're up next.
Yeah, thank you so much. So my name is Jens Böhmer. I'm with the Electric Power Research Institute. We are a not-for-profit research and development organization and dedicated to the public benefit. So in my presentation, I'll talk a little bit about interconnection study process and reliability implications and possible improvements. I would like to acknowledge the partial funding of our research here from the Solar Energy Technologies Office of the US Department of Energy. And depending on how we're doing here on time, I might share some preliminary thoughts regarding the FERC NOPR here specifically. And if we run out of time, then you can review those thoughts on the slide decks that will be posted tomorrow, I believe. Okay, so a couple of acknowledgements and disclaimers. So we, as a research organization, we do not provide regulatory advice. We do plan to submit comments here to FERC. Now, those comments will likely look similar to what you'll see here today in the presentation, but they are obviously subject to change until they're submitted. And when I speak here from a pre-technical experts perspective, that does not mean that these opinions or facts are all shared by our EPRI utility members and others who work with us collaboratively in research. And the same holds, obviously, that I'm not representing the US government here. So we all know why we're here. The processes are highly diverse and kind of backlogged. If you want to look at this publicly available EPRI report that compares many of those processes in the US, you can follow the link. Now, we also heard from Ryan Quint here from NERC that they're not only backlogged, but they kind of fail us in terms of ensuring reliability, which is not ensured in many cases right now because we see significant reliability issues with solar PV plants in particular. And when we look at the NERC reports to which EPRI and many other stakeholders have also contributed knowledge, we really see that those issues seem to be rooted in a mixture of insufficient inverter unit performance and insufficient plant design and configuration. So consideration of the interactions between the plant controller and the individual inverters and things like that is very important. And if we don't take care of that ahead of the construction and then the commissioning, we might run into big surprises. So that's important here for my presentation. This pre-construction design evaluation is really a concept that we see in other areas of the world being used much more thoroughly than here in the US. In the US, we have these 3 study types: feasibility study, which is mostly steady state; system impact study, which includes the stability analysis and is aimed at reliability impacts on the grid; and then the facility studies, which tries to break down a more concrete estimate and also identify electrical configurations for the specific interconnecting plant before it is eventually built. So the question really becomes, how can we improve both the process efficiency and at the same time maintain reliability? And it almost sounds as if it's impossible to meet both objectives, but maybe it's not. And I think we can learn also from other countries and regions around the world. So this FERC NOPR, quite significant, obviously, covers a couple of areas. And as I mentioned before, it's open for public comments, which I think are due on October 13th. In my presentation, I'm focusing solely on the 3rd and 4th topics, which are the incorporation of technological advancements into the interconnection process. And probably very important here, the update of modeling, but also performance requirements from a system reliability perspective. So I also had the privilege to co-lead together with Alex, who just presented this NERC inverter-based resource performance subcommittee subgroup on interconnection studies and process. And this slide summarizes some of the recommendations that came out of that discussion and that group. And I think it's worthwhile to spend a little bit of time going through these before we go into the details of the process here in the US. So the first recommendation from that group that had a lot of overlap with IEEE 2800 working group folks was that there might be benefits to do a paradigm shift where we really want to see the IBRs as the good citizen. And we can achieve that by integrating a unified minimum set of capabilities, even before such capabilities would all be utilized. And what that could mean is that adopting IEEE 2800 as soon as possible to really send the signal to require such technical minimum capabilities and performance can help generate a level playing field. And obviously the question is, how can a performance standard be implemented or adopted before the associated test and verification procedures are available? And those are important questions, but simply requiring these requirements can already send a signal to the industry, which I think we heard Divya mention that before, can also be very welcomed and helpful for IBR developers. So the second recommendation then goes down more towards the verification of the requirements. And the group felt that there are opportunities to improve the interconnection process, particularly with regard to pre-commissioning and also post-commissioning plant level performance conformity assessment. So I guess that's one of the reasons why we have this workshop here, so that we can exchange some thoughts on possible improvements. But then really important also the third recommendation, to increase education and collaboration and to think about these changes as a continuous process where we will iterate between improvements of IBR plant performance requirements, then improved modeling and model validation, which then can also inform future updates to performance requirements. So one way to contribute to that is to engage in the follow-up process in IEEE 2800.2, which is a recommended practice for the IEEE 2800 test and verification procedures. Let's look a little bit deeper into this here. The next two slides are quite busy, but let me try to summarize them as swiftly as possible. This slide shows some of the challenges that we have also heard during today's presentation in a succinct way. We have these different steps of interconnection request, the feasibility study, the system impact study, and then the facility study before the plant is constructed and then commissioned. Now, many times there are not very detailed or sufficient technical requirements available in the first place. And even in leading examples such as ERCOT, if you compare those requirements with, for example, the IEEE 2800 standard, one can still find a number of gaps that could possibly benefit from being filled. So if there are no sufficient requirements across the place that apply to the whole plant, then it's also very difficult, if not impossible, to submit any models that really represent those interconnections in the first place, and certainly not that early in the process where in many cases, as we have also seen on one of the questions on Slido today, it is not even selected which inverters are used. So in the second step, the feasibility study, many ISOs and TSOs are starting to implement screening in order to bifurcate some of their detailed requirements in the process, but that screening is still limited. And I guess the question is, maybe could increased screening help, whether at all, or what type of models and system impact studies would have to be conducted in order to interconnect the plant reliably. In the third step, again, we see a lot of these system impact studies being done with insufficient or invalid models. They're not site-specific, and even if they are site-specific, they start out being parameterized with generic parameters. So not necessarily suitable for a given connection point in the first place. Also, these may not really represent the actual units or supplemental devices used in the plant design. And then the question becomes, what value is there going through this step in the first place if that was not ensured? And then in the facility study, one can also say that right now the facility study has no scope to actually assess whether the plant is designed such that it would conform with the technical requirements set by the RTOs and ISOs in the first place. So there's no thorough IBR plant design evaluation, and that might be a gap. So when we go into the construction, some ISOs do have as-built plant level evaluation to compare whether the plant has been built as it was designed, but not all of them do that. And then in commissioning, it's quite tricky to actually run large signal disturbance tests without a lot of effort or impact on neighboring customers. So most of these commissioning tests are solely limited to small signal disturbances, and there's no verification of right-through performance at all. And many transmission planners also do not thoroughly collect field data. So even if there are some non-conformity issues, they might not be fully seen or not seen in the required level of detail and resolution. So possibly these IEEE standards, now that the first one exists and the second one is in the making, could help improve and fill some of those gaps. So if we looked at this in the working group from the NERC perspective, which obviously, is not fully representative, but there were a couple of ideas that were really important. One was that simply by agreeing on a technical set of minimum requirements, the expected performance of these plants can already be narrowed down significantly, and that could even help inform some of the modeling in the first place when there is still so much uncertainty about the actual equipment. Now, in the second step, maybe some screening based on, say, transmission hosting capacity maps or grid strength measures could help inform what level of detail of modeling might be required. And then the third and fourth step are really where there are opportunities to iterate. And I think we see this reflected to a certain degree in the NOPR as it was published, that any change of planned equipment might trigger a restudy of the reliability study. So that's something where the appropriate and sufficient and validated models based on the actual equipment that would be used in the field may become important. Now, to what extent that can be achieved without having a large generator interconnection agreement in hand, which often provides planning security, or to what extent maybe some form of a conditional LGIA might be needed in order to decrease the uncertainty of equipment in the field. That's something still to be figured out. But the point is that even between the step 4 and then the planned construction, there are opportunities to more thoroughly evaluate the design of the plant. Then once it is constructed, evaluate whether the plant was constructed and as built as designed. And then in the commissioning step, maybe some improvements to commissioning tests, but primarily focus also on the post-commissioning monitoring and plant level performance conformity. That is a continued process. So those are a few ideas. We'll see how this all shakes out. If we look at this, from the education perspective, obviously EPRI is working very closely with transmission planners, but there are also other forums to get involved, and I'll not mention them all here. You can look at that in the slides. Now, with maybe the last 2 or 3 minutes here left, if Roberto permits me, I do want to take a quick look at the FERC NOPR itself. I think we see this important area of update, modeling, and performance requirements for system reliability. Now, with regard to the performance requirements, one question is, could FERC even refer to existing IEEE standards? For example, 2800 for these large plants, but the NOPR itself also refers to smaller generators, in which case IEEE 1547 may be more appropriate. Now, it's actually interesting to see that IEEE standards are already referred to in FERC orders and even NERC reliability standards, and certainly many state PUC regulations when it comes to the smaller distribution-connected plants, because IEEE standards are available to anyone for purchase, but they are publicly available, and they have also been developed in a standards development process that is rooted in consensus, due process, openness, right to appeal, and balance. Now, referring to technical standards like IEEE standards can really increase the specificity and the configurability of performance requirements that may contribute to reliability significantly here. Now, ultimately, one would need a set of criteria to determine whether it is 2800 or 1547 that would be applied, especially to some of the sub-transmission connected plants. But maybe that's something not too much to worry about for FERC. With regard to the performance verification, that seems still to be one of the bigger gaps also in the NOPR to a certain extent. And maybe a reference to the evolving 2800.2 could be helping to fill this gap, since there are requirements, or likely going to be requirements, for type testing of the units, and also to generate measurement data for model validation, to include new procedures for plant level conformity assessment prior to the construction, as well as the mandatory as-built evaluation after construction, and then the continuous monitoring after commissioning. Now, one of the trickier questions may then still be, how can validated models be submitted with the interconnection request at a time when the plant equipment is not yet selected? As we know and have heard also in some of the questions, these inverters are often not selected until later in the process. Maybe even the standardization of the performance through these IEEE standards can help fill this challenge. I won't go into these other details. Obviously, it's very important to consider any changes with regard to models whenever there are changes in the plant that are significant enough. And then also the question, what happens to the plants that are currently in the interconnection queue, or even plants that already exist and do not perform as desired. So in conclusion, we see that inverter unit conformity does not guarantee plant level conformity. There's a step that needs to happen in order to translate one to the other. Also, plant level conformity assessment prior to the construction really requires validated equipment information. Now, that information could be modeling, but maybe it could be a set of checklists that could be sufficient to address most of the reliability issues that we have seen to date, especially if that is combined with adoption of IEEE 2800, which may lead to a common and sufficient plant design that can also potentially simplify the design evaluation. So transmission planners could develop these practices ahead of 2800.2 and then contribute to that process. And last not least, we do not have to reinvent the wheel. This is not new to many regions of the world. It is new to North America, but let's try to leverage learnings from IC, NSOE, the German VDE, FGW, AEMO, and also others. So FERC could fill some important gaps that have not yet been identified in the recent NOPR. And with that, I would like to thank you for your attention. And if you're interested in some of the EPRI modeling related work, you can go to this link. Thank you so much. Back to you, Roberto.
Thanks, Jen. So with this, I think we're going to go into the Q&A session. Everybody submitted 45 questions. We will not be able to address them all. So we'll try to get back to you at a later, sometime later in writing, answer all of your questions. In the meantime, for the panelists, the four panelists, there's some questions, and the first one, I believe, some European countries have higher penetration LIBR. However, we do not hear of so many events. What is the difference between them and our American system? Any of the panelists can answer that question.
Why don't we ask Alex?
Oh, no.
This company does a lot in Europe.
Well, the main difference is, in Europe, there's pretty well-defined, minimum interconnection standards, both across, the modeling aspects. What is a sufficient model? How accurately are these models that you're using in your studies being validated against products and things like that? So, we haven't really gotten there yet in the U.S. We're trying the NAGF standards, like Jens had mentioned in his presentation. IEEE P2800.2 is, the kind of a validation requirement. This is one of the subgroups that I'm working on, is trying to close that gap, such that, there's at least a minimum standard for how to do these studies, minimum standard for how accurate the models have to be, kind of a minimum everything, right? Minimum how to make those things into the product before they get commissioned, and things like that. So, we are lagging behind, but we're trying to do the work. It is ongoing right now in IEEE groups.
Thanks, Alex. There's another question here asking if why shouldn't we break down the system impact studies, like doing first power flows and then doing the dynamics? I'll answer that one real quick. There's several regions in the U.S. that are already doing that, breaking it down, and I know of many other efforts that are trying to do the same thing, provide the power flow, because that will provide at least some certainty to the developers so they can decide to stay in the queue or help us clear those queue backlogs that we have. So there's a lot of effort ongoing, and many regions are incorporating that into their process. There's another question here. This is for Ryan. I don't know if Ryan is present, but is there any appetite at NERC for developing standards regarding operating reserve requirements for regions that see high penetrations of VERs?
I saw that question, and I think maybe we can take it offline, right? We have standards that focus on balancing reserves, contingency reserves, adequate levels of frequency response. Those standards are technology agnostic and likely because of the nature of the reliability issue that's presented there. Personally, I think we can keep them technology agnostic. Got to carry sufficient reserves. The balancing authority is responsible for that role, right? And having enough reserves to be able to manage contingencies, frequency response, all those things, to maintain ACE within limits and your BAL, you know. So I don't particularly see that as an IBR specific issue, although entities are responsible for ensuring they're carrying enough reserves on a daily basis using the procedures they have available. So I'll just leave it at that, Roberto.
Yep. One more for you, Ryan, on NERC. They say, why does NERC promote reliability guidelines instead of compliance requirements for performance modeling and simulation of inverter-based resources?
So I think maybe there's, you know, I think it's good to step back, right, and recognize there are multiple forms of, you know, regulation, if you will, right? The way I explain it is you can advocate the goods or you can go after the bads, right? Advocating the goods, developing guidance material, et cetera, trying to identify faint signals and address those faint signals before they become systemic issues. I think we've done a tremendous job at trying to do that, raise awareness of these faint signals and work with industry to take action to avoid the need for regulation, right? But what we've identified going through these disturbance reports is that industry is not taking action, right? And issues are not being addressed at the interconnection process in particular, right? Which has led to a large handful of standards authorization requests, standards projects that are now underway to drastically enhance the standards, and all the way up to our, you know, board of trustees level. They're paying close attention to making sure we move the needle from a regulatory standpoint adequately to minimize or eliminate the possible risk of a really bad day, right? Particularly related to the IBR risk issues, right? So we've kind of worked through that spectrum, and now we're really focusing on enhancing the standards and then, you know, enhancing our risk-based compliance approach so that we are making sure we're actually sufficiently auditing, working with our regions to identify risks that could be present out there based on what we've found on the engineering side. So likely see more of that coming.
Thanks, Ryan. Jens, you have your hand up. Do you have a question or?
I was just thinking, you know, Ryan's thoughts a little bit further and looking across the US borders a little bit more. I think we've seen in various regions different approaches, but I think a tendency is that whenever it becomes clear that the industry has not been able to reliably self-regulate on some of these reliability issues, something that is kind of scary to engineers happened, namely that the policy level has started to pick up on some of these things. And you know, we know in Europe, I think it was up at the European Commission and then policy level that they passed some pretty specific grid code or technical requirements, which obviously were then implemented slightly different in the various European countries. But I think it's important to recognize that every stakeholder in the industry has a responsibility to really try to engage and kind of embrace some of these more specific efforts to define technical minimum requirements, because otherwise somebody else will do it. And it's always a good thing if the engineers end up doing things based on understanding. Thank you.
Thanks, Jens. There's another question here. Some OEM EMT models are proprietary and covered under NDAs, which prohibit sharing. Are publicly shareable standard EMT models available? Some of this has been answered in the chats, but anybody wants to chime in here?
Okay, this Jens, let me break the ice. So I think the question becomes, what defines a standard EMT model? And obviously there are efforts in different organizations, including some joint SIGRE and IEEE efforts to at least harmonize some of the structures related to models, then also related IEC efforts. Now, here in the US in particular, some of the, let's call them authorities that have recognition to promote and approve certain models are certainly NERC and then WEC, the Western Electricity Coordinating Council. And at least at the WEC, there are some preliminary efforts to explore potential value and specification of generic EMP models. Generic EMP models in the sense that they would still have to be configured site-specific to the extent possible. But I think we also all understand what Alex had said in his presentation, that the nuances in the EMT models can be so vast based on the individual vendors' proprietary control concepts that a generic EMT model may not fully represent an OEM-specific model. Now, EPRI is doing some efforts in the realm of generic EMT models. If you go to our website that I shared, you might find some of those. But I think it's definitely something to consider, but still with a grain of salt as with regard to the application cases of those.
Thanks, and I'll chime in a little bit. Does somebody want to add it? Oh, go ahead, Alex.
Oh, yeah. So I was going to give just kind of the OEM perspective here, right? And just in general, in the EMT domain, even, performance in general is protected in IP, right? So even if there was a generic EMT that was performance validated against, real measurements and things like that, that would also be shared under an NDA. And, really at the point we're at now, how EMT models are used in the process is, they're treated basically the exact same way as an RMS model is. When we share an NDA or a black box model with a customer, our NDA says, please share this with your consultants, please share it with the, the TSPs and the ISOs. Just those of you who are receiving it, and if you're sharing it, please share it, in a secure way and protect the IP there. So, even RMS models now that are site specific and site parameterized, the performance of those are treated as CEII most of the time. So, in general, they're treated the same way. It's just because it's a black box model doesn't mean that nothing is available and it's just, magic happens behind the scenes. It's a black box model, but all the relevant control parameters, all the relevant tunable parameters and modes and things like that, as well as documentation of how to set those up, all of that comes with it. So just because, I want to make sure that when we say black box NDA protected EMT models, it doesn't mean you have no idea what's happening behind the scenes. It's just, we want to make sure that the IP is protected, but we're also under that same NDA, let you know, here's how you configure it, here's how it works, and here's how to get everything up and running.
Yep. Thanks, Alex. And I'll just put in my couple of cents here. On the EMT, it is pretty challenging to develop a standard EMT because right now the challenges we're seeing with our generic models for power flows and positive sequence is that it doesn't give us the accuracy we need for the specific plant. Developing a standard EMT, we're going to end up in the same place. We're not going to have the specificity of a plant design that we're seeking to understand and build until we have it matches the real construct of the plant to the EMT. So it may add a little bit of value, but it's not that significant, and the effort is going to be monumental. So yeah, I'll just take it with a grain of salt, like Jen said. Developing those EMT just for reference, but they're not going to be more meaningful than the current studies we have for dynamic studies on positive sequence. And we will have, I think we have time for one more question. This is for Mario. What are the requirements for the UMV validation in terms of lab requirements, test scenarios, and metrics to quantify how we model matches hardware? How well models matches hardware?
I don't want to pull a Jim and be like, Alex, you can actually answer this question.
No. Go ahead. You want me to answer? I can.
Yeah, I mean, I think you're going to have a much better grasp of sort of the UMV in terms of like sort of how the lab tests are set up.
Yep. So I mean, we've always done unit model validation against the hardware in the loop, but it's become kind of more prevalent now that ERCOT has added it into one of their requirements. So basically, what we do is for one PPC software type, each turbine kind of platform, what we do is we basically put that turbine and PPC in a what's called a hardware in the loop. It's kind of like a test bench, and we run a bunch of tests. We run active power set points. We run reactive power set points, voltage set points, faults, and things like that. And what we do is we show that, hey, here's the results from the hardware. Here's how the actual hardware is responding. Here's how the EMT model matches it. Here are all the parameters in both. For Vestas particularly, it's the same parameters. They're one-to-one matches. It's the same code, same parameters. So it would be basically what we provide for our ERCOT plants and anyone else who really needs them in the U.S. It'll basically be a hardware in the loop test. All those tests I mentioned. So you get the actual product, you get the EMT, you get the RMS tools that we use, TSET and PSSE. And we basically show, hey, here's all 4 plots. Here are all of the performances. Here's how they all match. There might be some small discrepancies. Maybe EMT is filtering slightly differently, or maybe the EMT has more mechanical features that you can't capture in RMS simulation. But all those descriptions or all the discrepancies, I mean, are described. But in the most part, we show all of them and say, hey, our RMS matches the EMT, our EMT matches the product. So assuming that you do your studies with your model and you put those settings in the plant, you should expect and trust the model response.
Thanks, Alex. And with this, I think we're out of time. I'll just wrap up real quick, summarizing that the interconnection studies, the quality of them, and the reliability of our system should be the most important aspect of the interconnection process. I hope that FERC and other entities, bring that to the forefront and give it the most value to this, because with this, we will have a reliable and system that will last us for a long time and will allow us to interconnect any type of technology. Julia?
Right. Thank you so much. Thanks, Roberto. Thanks to all presenters and everybody who posted questions. Great questions there. As a reminder, we'll address all unanswered questions, and we'll post them on the event page. We'll also post all presentation materials and the recording presentations on our event page and recording on our YouTube channel. And we'll reconvene at 2:45 Eastern time. So now we have a short break.
I'd like to welcome everybody back to our second session of the day. This afternoon will be focused on the importance of modeling. I am Lauren Hughes. I'm the project manager here for OAT Interconnection Studies at Southern Company. So we have 3 great speakers lined up for this afternoon. We will get started, though, with Puyan Porbek, who is President and Principal Consultant at Power and Energy Analysis Consulting and Education. So with that, a reminder, everyone, we are taking questions on slido.com. You can see the event code there on your screen. And with that, I will turn it over to Puyan.
Thank you so much. Can you hear me okay, Lauren and others?
We can hear you.
Okay, I turned on my video just to say hi, but I'm going to turn it off so not to kill my bandwidth and mess up the voice. And I will try to share my screen. A second. Okay, can you see it okay? Is it big enough? Does it need to be bigger?
Yes, we could see it.
Okay, perfect. So as Lauren, Julie, and others said, we're going to talk about the modeling piece. So I'll start off with this slide, and kind of ended on modeling from the last session. Just some food for thought. Your models have various uses. I'm sure there's more than even what's on this slide, but the main things we tend to all talk about, we've talked about these past sessions, is power system planning, post-disturbance analysis, equipment and plan design. I will offer that some models get used in all three spaces, and yet each one of these spaces has models unique to its own needs that are not necessarily used in the other. Just one example is if I'm looking at a 10-year or 5-year horizon planning case, I may be using models of things I don't even know who or what the vendor is going to be. So I can't be using very detailed plant design information because I don't even have it. Vice versa, in plant design, I have to look at details inside a collector system, which when I get to system planning, I don't necessarily care about. I assume the plant has been, and I must assume has been designed properly so that there are no issues inside the collector system. And we all know, even in EMT world, doing system studies, the model is aggregated. So it has an aggregated representation of the collector, not a detailed. Yet for equipment and plant design, I need the detailed model. So there are things we need in each space that are different to the other, just to be cognizant of that. So there is no one perfect model. That's a figment of human imagination, not a reality. The other thing is, and we've kind of talked about this, but brushed over it just to bring us back, hopefully on the same page.
Jan, can you go to full screen, please? Just a little bit too small.
Yep, I can. Give me a second. I gotta fix
Thank
something
you.
real
That's great.
quick here. Duplicate. Is that better?
Much better.
Okay, perfect. So, this story has never changed. This has always been true, whether inverter or no inverter. We have this wide spectrum of phenomena in power systems. These have always existed and will always exist, from very fast transients like lightning and GIS transients to unit dispatch, which takes place over hours or days. Again, depending on where I am in this bandwidth, I need different models. I'm not going to use an EMT model to do unit dispatch. I could do it, but it's like using a Ferrari to do the job of a Toyota. It's very expensive. At the same time, I'm not going to use a production simulation tool to study lightning because I can't even do it. So we have to again recognize that going into a problem, we have to have some idea as engineers using our judgment where the problems might lie. We cannot go into a problem blindly and have no idea of what we're interested in. We know what we're interested in, and therefore we pick the right tool for the right task, and therefore the right model. So that said, these are the genre of models. I'm not going to spend time on it, but and there are things in between each one of these bullet points. But so again, depending on what are we doing plant design? Are we doing planning, forensics? What part of the bandwidth we're worried about? We'll pick which one makes sense, and we'll use it. Do we need hardware in the loop? Do we need EMT? Do we need real code-based user-written models? Is a native software language user-written model adequate, or can we use a parameterized generic model? So that said, now let's talk about modeling, because as we all heard, it is important and we have to get it right. So what do we do with these IBRs? In the industry-wide and somewhat globally wide accepted approach is that we develop these aggregated models when we're dealing with the planning side of things. And so we take, there's my pictures of the physical equipment and how we boil it down. Take the pad mount, transformer. This is for a wind plant, could be a PV plant, could be whatever. And we aggregate that into an equivalent generator step up. We aggregate all the wind turbines, assuming they're the same technology, into an aggregated wind turbine model. We then collapse the collector network into equivalent feeder using either the NREL method or there's another method ERCOT uses, their equivalent. And then everything else we model explicitly, the substation transformer, the shunt banks at the substation, or if there's a STATCOM or whatever. That's the model we use, whether we're doing positive sequence, EMT. That's the model we use. The one caveat is, of course, it's not always a single aggregate. Depends if we've got multiple technologies in a plant, like half wind, half PV, or two different models of wind turbines, or sometimes two substation transformers and the turbines are grouped separately on the substation transformers, then we need multiple aggregates and multiple feeder equivalents. But that's kind of perhaps, hopefully, somewhat clear. Now, a question may be asked, well, is that adequate? Yes, it is. Of course, there's limitations. And the one limitation is what we said on slide 1. If I'm interested in detailed design of the collector system, then the aggregate is not adequate. It's not going to give me the voltage profile in the collector system. But if I'm looking at things from a system standpoint, the model is adequate. And I've given a reference there from back in 2011, where Hydro-Quebec did a detailed, using supercomputers, comparison of modeling every single little component in the plant in the EMT and broke it down into everything modeled to gory detail, then 5 machine aggregate, 3 machine, 2 machine, 1 machine, and showed that the POI, the electrical response, was almost exactly the same. So again, if we're interested in looking at it from the POI, looking into the plant, how's the plant interacting with us, then that aggregate is adequate. And here's again real life measurements. So what I'm showing you here is just snapshots, agreed, but measurements at 3 different plants of P, Q, and V measured and simulated with the aggregate. I won't sit here and go through every point, but if you look to 2 significant figures, in some cases they're almost exactly the same. In other cases, they differ in the 3rd decimal point by a little bit. Am I going to kill myself over that? No. And likewise, here's an example where we didn't have to, but we deliberately measured individual turbines in the plant while doing the test at the POI. And you can see again, the general dynamic behavior of the individual turbines in the plant mimic what you see at the POI. Some cases almost exactly, I think just got lucky. But in reality, there are cases where there's offsets in the Q and V, and that's to be expected again, because look, as we said, we can't represent the entire collector system profile by a single equivalent impedance, but the dynamic response is the same. So there's just some evidence that yes, this single aggregate is a reasonable approach when we are concerned with system impact and how it's impacting us at the POI. So then what's the approach to model validation? You heard other speakers talk about IEEE standard 2800 2022 that's come out. I personally think it's still a little too early to adopt, because I tend to feel that 2800.2 needs to come out with the guidance before we can have a unified approach on how to adopt it. But looking at what's going on in 2800.2, you can already see an approach coming out of it. And this is not yet agreed to, it's still in dialogue, but it represents things that have been done to some extent to date. It's an approach already in some ways being applied. And the idea is you do unit level individual IBR, so individual wind turbine, individual PV inverter, individual battery inverter, what have you, type testing, say, for example, in a factory. And you verify the model of that individual thing. So once you're happy, you move to the next bucket or box where you build that plant aggregate model that we just discussed, both in power flow and dynamics. And then you say, okay, now I have to test and validate that the plant controller and the overall plant responds the way in the model, responds the way I would see in the field for things like volt-var and primary frequency response, and etc. So then that piece you do test in the field at the actual plant. And then just following that into the future, you can always monitor and do post-commissioning updates where you monitor, and if a grid event happens, you take that and play it back into the model and see if the model still behaves adequately. And that then gives you a complete picture. So it's a piecewise process, but it covers all the bases, because you cannot test, voltage right through in the plant. You're not going to go put a three-phase fault POI and see plant right through. So you have to rely on that unit level pipe testing, building the plant model, and then taking the fact that, okay, my unit level models must be accurate because I've tested those. And so if I built the aggregate and just put some evidence that the aggregation process does work, then I've got at this second level a good, nice plant model. I can test that plant model to see if it rides through and it's all good. Then if I want to verify that its plant controller is doing what it would do in the field, I can test that in this kind of purple box. And just so put some pictures to the words, here's some examples. This is from past work, but it's the same concept. So you see you have different vendors, equipment, just showing one plot, but there were tens of dozens of cases tested in the factory, or in this case, it wasn't factory, it was field tests on an individual turbine in the field with a basically shunt and series reactors. These are IEC tests done at the terminals of an individual inverter. And you see the response in blue, measurement, real power up the top, reactor power on the bottom. So we're putting, so to speak, fictitious faults at the terminal of the machine or the inverter, and then the simulated is the red. And in these cases, the simulated are out with parameterized standard models. They're not black box. These are written models, and it's good fit. And I'm only showing you one, but there were dozens of voltage dips done with the same parameters and pretty good fit across all of them. Then you have another vendor. Is yet another vendor and a PV vendor, same story. So this is, if you will, we've now done our first box that I showed previously. Let me go back to it because I remember. So we've done our, this is green, our sort of green box here. We've done our unit level test and verified our unit level models. So we now build our purple box. We build that model of the plant, the aggregated model. Then we go into a field test and we say, okay, can we now verify that the plant model responds the same way as the actual equipment response in the field at the POI for a volt-var test and a primary frequency test? And there are multiple ways you could do this. You could actually do it with voltage reference or frequency reference step tests, or you could do it if you had it by switching a large cap bank somewhere close to the point of interconnection to cause a fictitious voltage change at the POI. And you could do it with disturbance monitoring, like we said, post commissioning. So here are examples. Example of doing a voltage reference step test. So it looks good. Here's an example of doing it with, in this case, coordinated with the TO. There was a significantly large transmission capacitor right close to the point of interconnection of 3 plants. And so switched it in and you can see all 3 plants there, megawatts, megavars, and voltage. And you can even go down and look at the individual turbine stuff, and it all seemed to behave well. And now frequency response, again, same thing. We can either use a standard library model, and here's an example of standard library model, injecting a frequency reference step test measured versus simulated. Here's an example of a large plant, IBR plant, very detailed vendor-specific user-written models for the individual IBR units and the PPC, and doing a frequency step test again. Again, you get a good fit. Is this better than this? They're both good. And here's an example of disturbance monitoring. So a frequency event was captured, played back into the model, and model seemed to match measurement. So again, it's what we would call a pass. It's passed its validation. So one more time, it's just this kind of tiered approach of going unit level type testing, build the aggregated model, the large signal things you want to look at. Your best bet is to look at it with that accurate aggregated model. And then for general volt-var response, primary frequency response, and future FFR, you can do that with field tests at the plant level. Don't forget about monitoring post-commissioning updates to kind of monitor. I mean, let's say you did a monitor, you did one of these things, and the thing didn't match. Then you would have to question, say, okay, did something change? Did someone upgrade a software and not tell us? Did someone change out something and not tell us? And we have to go back to step one and ask the questions and go through the loop again, possibly. And that's kind of what I'm saying here. So really, to me, the conclusions are modeling is important with good and useful models. Proper model validation is also important. Knowing which models to use and where is extremely important. And keeping an eye always out for moderation is also key, not to get stuck in the details so much that you lose sight of what the purpose of the model is. At the same time, not brushing over simple things yet important details. And an example is sometimes one has seen, people will spend hours getting into the minutiae of little things on these, turbine level stuff and completely miss getting the tap position of this transformer correct. And if you do that, you've completely messed up the reactive capability of that plant model. So don't overlook simple stuff just to get stuck in details and completely mess everything up. So one should just always keep that in mind as well. That's it. I hope it wasn't too quick. I wasn't over time. I tried to stick to my 10 minutes or what have you.
Yes, thank you, Puyon.
Yeah.
So next up, we have Deepak Ramasubramanian, a technical leader at EPRI. So Deepak, I will turn it over to you.
Thanks, Lauren. Can you hear me?
We can hear you.
Thank you. Confirm that you see my screen.
We got you, Deepak. Thanks.
Awesome. Thank you. So, hey, everyone. It's a pleasure to be in this call and make this presentation at this meeting. Kind of following up from what Puyan presented, and I think also dovetails nicely with the discussion of the previous session. What I'll be talking about today is some of our experience on improving the IBR models and trying to understand the different modeling needs that exist in the various simulation software that we use, and try to provide some perspective on how we can go forward with improving the way we have these models represented in these various software, be it's generic or user-defined, it doesn't matter. It's about the functionality that we can represent in this various software. So I can move to the next slide. Yeah. So the work that we do when trying to develop any kind of new model and the process that we follow with developing or understanding how to develop models is pretty much we have the aspect about lab testing and field data to use in order to identify or really understand where the gaps are. So in some ways, the event data or the plots that Ryan showed really help us understand where models may have limitations. How do we use how do we use that information to really improve the state of the art of models that we can have in our various software and move along the process of really identifying how to even verify and test the models that we have? How do we ensure good model validation is obtained across the software? And not just pertaining to only stability and EMT domain. This even goes beyond to domains like protection, trying to understand power quality, and even trying to do some kind of longer term studies as quasi-static studies, and then take those model or take that information that we have and see if it applies to going into the library of a certain software, or if it applies to providing equipment manufacturers with insight on how they could potentially improve their models if there is a limitation that has been observed even in user-defined models. No model is perfect. Every model has scope for improvement, room for improvement. So it's how we keep improving these models is how we tackle our research. So on that note, I like to put this slide up on any presentation that I talk about models, because it's important to get this understanding that a generic model is not always a bad model. So just the connotation of a generic model does not always imply that it's a bad model. At the same time, a connotation of a user-defined model or a UDM from a manufacturer doesn't always imply it is a good model. There have been numerous instances where the opposite has been obtained for both generic models and user-defined models. The same thing applies to positive sequence domain and EMT domain also. The mere connotation of positive sequence domain doesn't always imply that it's a bad model. And the mere presence or sufficiency of having an EMT model doesn't always imply it is a good model, as some of the recent events have shown us. So all these models have their limitations, and there's a place for every type of model. It depends upon the type of study being done. It depends upon what kind of scenario is being studied. And it also is one needs to consider if we are using the model in a correct manner. So for example, there have been instances where a wrong model has been used to replicate or denote a behavior of a certain type of source. So which means that you're not using the correct model, and that can cause very different behavior to be observed. We also have to really talk about parameterization. Ryan mentioned this, Jens mentioned this, Bojana and Alex also mentioned it, that parameterization of a model is extremely important. One cannot assume to use default parameters. One cannot assume to use generic parameters. One has to have site-specific parameters for the particular model that is being used, and whether that model is user-defined or generic, parameterization becomes extremely important. So as we are going towards this new paradigm, in my presentation, I'll also be talking a little bit about this concept about how we can go towards newer types of inverter resources. What is the aspect related to modeling these resources? And just one slide talking about current source representation, because we heard about modeling the resource as a current source and having it inject currents into the network. It's useful to take a step back and take an overview that Kirchhoff's law still applies in a 100% current source network. So just because we might be going towards a scenario where there is representation of current source, there's no real aspect of Kirchhoff's law really failing. Now, yes, it does depend upon how you inject those currents at a given point in time into the network, but the way in which we change that current injection really plays a role with respect to how we represent these devices for our planning study. So what does this all have to do now with IBR models? So present state-of-the-art models are represented as current sources in our simulation software, especially positive sequence software. So the next few slides will be about positive sequence software. Present inverter models are represented as current sources. Now, that by default doesn't mean that current source is bad. It comes down to the representation of the model in the simulation software. And we have seen that such models may have limitations with trying to represent fast controller dynamics. So especially if you see a scenario such as this, wherein you have a deep fault and you have 3 different positive sequence software showing a similar trend of a false positive response, whereas you see an unstable behavior coming up in an EMT domain software. Now, these fast controller dynamics and interactions, there is a limitation in the old set of models. And when I say old here, I mean until 2 years back. So in the models that were developed until 2 years back, or the models that were present until 2 years back, there were these limitations with respect to representing these fast controller dynamics. And there were also numerical robustness issues that may arise in those models. So a few of you may have used these models in the software. You might have seen messages like network non-convergence coming up in your screen when you use such models in the software. Now, again, one needs to keep in mind here, if we go back to the first slide where we said every model has a place, the model needs to be appropriately parameterized, the model needs to be appropriately structured and developed. So just the presence of these kind of behavior doesn't automatically imply that EMT studies are the only solution available. They are definitely one solution one can pursue, but it also gives us insight into how to improve the models in the positive sequence software that we use. So we go down from the perspective that if every inverter for power system operation is a voltage source inverter. Now, again, let's not confuse this with terminology that you may have heard regarding newer technology like grid following or grid forming. Let's keep in mind that every inverter that we use is a voltage source converter or a voltage source inverter. But a lot of the models in today's interconnection-wide simulations, they use, and be it generic or user-defined models, may represent the inverter as a current source interface. And what happens because of that is they assume that the current controller and the phase lock loop dynamics are fast. Now, this assumption is all right for strong networks. But when you start coming towards weak networks, when you start looking towards low short circuit scenarios, this assumption that may be there in either a generic model or a user-defined model that the current controller and the PLL loops are fast, that assumption is not necessarily going to provide a robust. So the simplification that comes up with this assumption doesn't necessarily provide a stable result or an accurate result. In fact, how inverter-based resources should be represented, even in positive sequence domain, is recommended to be represented with a voltage source interface such that you can have greater accuracy and characterization of inverter-based resource dynamic behavior. And for traditional inverter controls that may use a current controller and a phase lock loop, it allows for the representation of these kind of loops. And an example is so, wherein if you look at the traditional model, which has been called REGC_A, it could provide a false negative result in a certain scenario, wherein if you compare it with an EMT vendor model or a black box model, there was a stable response. Now, as a planner or an operator, you might say that, hey, it's okay to get this false negative result because it gives me some indication that something might be happening in my system at this low short circuit strength, and I want to do a detailed study. But if you have too many false negative results, and if you do an EMT study, then it can lead to an overconfidence or can lead to a complacent behavior to say that the next time you see a false negative response, you might just brush it off. I'm not saying you would, but there can be a tendency to do it, similar to the fairy tale story of what we've heard in our childhood regarding the boy who cried wolf, that the third or fourth time after he cried wolf, the villagers never came to help him. But that was actually a real scenario where they needed help. So having improved models that can provide not just an accurate behavior of stable response, but also provide a representation of an unstable response is what we want to achieve with improved models. So with this voltage source interface representation, with having improved representation of current controllers, phase lock loops in the models, now we can start to achieve, even in positive sequence domain, a representation of the instability that might arise in the for low short circuit strength behavior. Will it be a perfect representation of the instability? Most definitely not, because there are so many other simplifications that we do. But however, having this representation now allows the planner to have more confidence in their simulation result, such that they can then take this and then carry out a more detailed study for locations where they need to do. An anecdotal fact here is that the user-defined model that was there for this particular plant couldn't show this oscillation. So which means to say that there could be something else. There's an assumption made in the user-defined model which needs to be improved upon, which needs to be developed further so that we can overall improve our state-of-the-art of modeling with respect to inverter-based resources. The other aspect with respect to inverter-based resources is we have seen events wherein DC side dynamics have played a role, and we can have tripping of inverters with respect to DC side dynamic behavior. Now, in a positive sequence model, it is conceptually possible to capture these DC side dynamics. However, whether it is required for certainty or not is only possible to know after we do detailed studies. So we have to keep in mind that conceptually it is possible to capture this. And this is all from the perspective of the ability of the simulation domain to capture these behavior. We're not saying that the models today already have all this. This is looking forward to the future to try to understand where improvements can be made to the models that we use and how we can really incorporate more features into the models that we use so that we can get a better representation of the dynamic. So I'll close out with this slide that we prepared, looking at the various events that have happened and really trying to understand what are the causes of tripping that were observed in various kind of events. Now, certain causes of tripping, such as subcycle, over voltage or under voltage, over current, unbalanced conditions, and so on, they are definitely out of the realm of simulation software like positive sequence or RMS. So we shouldn't even be trying to capture such behavior in the software. But other aspects of tripping, there is a possibility that future models can capture, and we have to push the research domain in that space so that we can improve the overall way of capturing these representation. We have seen in these reports that even the EMT models that were available to the planners, they also couldn't capture some of the causes of disturbance because they also may not have some features that were needed to capture this kind of tripping that may occur, which also points to the fact that we need to improve our state-of-the-art of models across the whole simulation space that we use. And diligent parameterization is not a facet that's needed just for positive sequence. Diligent fast parameterization is needed even in the EMT domain. And model validation is also not just a facet that's needed only in one domain. We really need to have good model validation across all types of models that are used. One cannot assume by default that one particular type of model may be good or validated just by default. One has to have model validation procedures that could be put in. And we have to also understand that when we develop these newer positive sequence models, it's not to say that it's a replacement of EMT domain. It's not to be even construed as that's the indication. What it's meant to do is it's meant to complement the EMT domain studies that are increasingly becoming important. It's important to start collecting EMT models so that in the future, when such a study needs to be done, the models are available to carry out that kind of study, and then use these newer models, newer positive sequence models, to get a better understanding and get a better picture of how these resources may be. So with that, I'll just close out my presentation. Hopefully I stuck to time, Lauren.
Yeah, absolutely. Thank you. So we will move right along to our last speaker of the session. And next up, we have Brad Marszkowski, a senior engineer at ISO New England. So Brad, I will turn it over to you.
Hey, great. Can you hear me, Lauren?
We can hear you.
Sound check. All right, wonderful. Yeah. Turn that on. So, hi everyone. Thanks for the opportunity today to discuss EMT studies. So today I'm going to give you a small background on kind of what an EMT study is, how it's different, from a positive sequence type simulation. And then we'll get into when ISO New England does EMT studies, a bit about our study practices, and we'll finish off with a short discussion on EMT models for IBRs. So, what's an EMT study? At the core of an EMT study is just a study that uses time domain solutions of the differential equations that govern the element's responses. There are many different methods for solving the differential equations in the analysis, familiar ones like Runge-Kutta methods or trapezoidal integrations. Each have their own pros and cons, and different softwares like PSCAD, EMT, PRV, and MATLAB use their own types, but they're really all being used for the same purpose, and that's to solve the differential equations that model the electromagnetics of each individual element's differential equations within the system that you're studying. Because they're integrating these kind of differential equations that you see at the top there, you can use these very small time steps, and so very fast switching phenomena can also be modeled in these types of studies. Now, this is different from traditional phasor-based calculations in transient stability programs, which are based on positive sequence models. Positive sequence models are abstractions of the full three-phase system. Traditional positive sequence simulation programs assume a balanced system, and so they ignore sequence contribution or zero sequence contributions for unbalanced phenomena. And they'll also normally assume a fundamental frequency and ignore the effects of frequency on frequency-dependent elements. This is partly why they solve normally around a quarter of a cycle, because they're not really meant to model faster phenomena. And so by making these types of assumptions, the element and the system equations become algebraic expressions, which are much easier to solve, and so they're far less computationally expensive than in the EMT case, where you're integrating the differential equations with very high resolution for each element. So why do an EMT study? Well, the crux of most transient stability studies is that they're not really capable of modeling all of the behavior that exists on the grid. Now, no single model really is. Even EMT studies have their limitations, as Deepak just pointed out. However, EMT models can get you much closer to the real physical behavior on the grid. A positive sequence RMS, fundamental frequency simulation, is not going to show you the real-time response of an element, as the simple example on the screen shows. This is just a capacitor switching. Now, imagine, if you will, you have many different capacitors, different inductors, synchronous generators, power electronics-based machines, etc., all over the system. Each element having its own time-based response. You're going to have a lot of different interactions. You're going to have a lot of different signals all competing. And traditional transient stability simulations, as you can see here, are just not capable of capturing all of that detail, which is okay. They were never meant to, right? They're great at what they do, which is large system stability. They shouldn't be used to try and capture this kind of stuff, right? It's the right tool for the right job. But EMTs are much more capable of modeling not only the actual physics of the elements, but also the logic and the software-defined functions that are part of the types of resources we're seeing interconnect today, mainly inverter and converter-based resources. This is because the EMT simulation softwares, or at least the ones I'm familiar with, are full three-phase representations and can model things like frequency dependence, mutual coupling, really these logic functions that are based and derived from three-phase quantities. So all these new resources are power electronics based and use switching elements to control voltage and current. Since the differential equations can be solved at very small time steps, much more of the switching behavior and functions tied to that switching behavior can be modeled. As pointed out, earlier when Ryan was talking about the NERC disturbance reports, it was pointed out that the functions in logic that are not able to be adequately modeled in most transient stability programs have actually been responsible for the events that transpired in those reports. So this example kind of gives you an idea of why that is. Again, you can see here that there's a whole host of dynamics associated with the EMT output, but all of this is really abstracted when it comes to the RMS output. In EMT space, a study can be run to understand those unbalanced phenomena, harmonics, transients, and other very fast and high fidelity phenomena. So that's just a quick introduction to what an EMT study is, why it's important to run them. EMT studies, in general, are just going to give you a much better understanding of the behavior of an IBR than a stability study can. Similar to how Alex was pointing out earlier. I think I just lost connection.
Oh,
Brad,
we
would
can
you
still
Yeah,
hear you.
unfortunately, I just lost my slides.
Okay. Brad, this is Ryan. I can advance them for you if you'll let me know what slides you're on right now.
Sorry, give me 1 second here. This connection restored, but it hasn't come back up yet. Sorry, bear with me for 1 minute here. Okay, I think I'm back. Just so we can keep moving forward, Ryan, would you mind jumping to slide 6 for me? There it is. Apologies for that. So ISO New England requires EMT studies to be done as part of the system impact study for every new inverter-based generating facility or elective transmission upgrade that utilizes power electronics as part of the facility or a network upgrade. Think of things like VSC, HVDC, and where they're adding a lot of stat comms in order to add a lot of reactive support. So I've listed here some of the different reasons to do an EMT study. These include, when you say you have a large IBR connecting to a weak system, that IBR can push the system around a bit, or a low SCR condition. We're looking for things like unit stability, again, like Alex pointed out in his presentation earlier, where they had a SCR of like 1.75 and it was doing weird stuff. We're making sure that speed of responses don't cause other issues on the system, like under voltages being caused by overshoot. There's a lot of different things wrapped up in weak systems. For SSTI and SSCI, we're making sure that the IBR's control designs don't adversely interfere with other nearby resources or cause any sort of high frequency oscillations. If a control design is poorly designed, it can sort of do this push and pull against other resources and cause oscillations. from the synchronous generation world, most folks would probably refer to it as hunting. We're also looking for the obvious things like voltage ride-through and other large system disturbance responses, like making sure the PLL stays synchronized or the DC bus doesn't have an overvoltage condition, which makes it trip, or that current limits are set properly and so it doesn't trip for a design fault. We're obviously also looking for transients. It's kind of in the name, electromagnetic transients. We're making sure that there would not be trips for certain instantaneous overvoltages. So these are the kind of things that really you're only going to see in an EMT study. I mean, some of them you might see different versions of in a transient stability study, but for the most part, you're going to get a good understanding of this in EMT space. As again, with transient stability simulations, they're highly abstracted and lower fidelity than in EMT space. So these different types of studies are mainly dependent on the highly specialized and tuned controllers that are unique to each OEM, and so they can be missed by using generic models and studies. Go ahead and switch the slide here. There we go. All right, so let's talk a bit about ISO New England's EMT study requirements. At the ISO, we use the Manitoba HVDC's PSCAD software. It's been around for a long time. It has a lot of the features that we like, and we've been requiring studies in it since around 2014, I believe. As I mentioned previously, we perform the EMT studies as part of the system impact study for all interconnection requests for inverter-based sharing facilities. The study will normally include both N-1 and N-1-1 testing to identify low system strength concerns or other ride-through issues. Case setup will normally start by converting the ISO New England developed stability case that was originally used as part of the SIS for stability testing in PSSE to a PSCAD case using ETRAN. We'll then add information that was originally not included in the stability case, like more the transformer information, like transformer saturation, frequency dependency of lines if needed, manufacturer specific models, since we mentioned earlier, or folks mentioned earlier, that it's not really generic EMT models, et cetera. So we'll add models for both the project under study and all relevant resources within the electrical proximity. Now, we can't convert the entire Eastern interconnection case and try and run it. So instead, we create boundaries and add voltage sources with a certain strength at those boundaries. All these decisions are done during scoping, of how large to make the EMT case, the PSCAD system under study. But we'll essentially expand the system to the point where the project under study and all relevant projects within sort of an electrical proximity are included. We make the decision based on essentially the amount of impedance between the area under study and those boundaries. There's a lot of engineering judgment that goes into this. When we go to run these cases, we'll actually then start with the initial conditions pulled from those original PSSE stability cases. And so the initial power outputs, the bus voltages, angles, all that will come from the PSSE cases. Using ETRAN to convert the cases in this way saves us a lot of time in the case building, since all the topology is directly ported over. This also gives us the ability to perform benchmarks between PSSE and PSCAD to better understand what type of phenomena we may be missing in the stability studies, or vice versa in the EMT studies, for the much larger system, the Eastern interconnection-wide system. So, once all that's in place, we can then sort of iterate on those models and make sure the, new interconnection is robust. So, it's a bit about, how we set up cases of study requirement and what we do during those studies. But, any good study starts with models, right? So let's go over a bit about, initial model requirements. As I mentioned previously, all system impact studies for new interconnection requests involving IBRs require an EMP analysis. So, I just realized my video is off. Or is it still on? internet problems. So we require all new interconnection requests to include an EMT model that's usable in PSCAD. The models are vetted for things like accuracy, usability, and efficiency before the start of the system impact study. These are things that we can check for ourselves by just putting the model into PSCAD and running it in a SMIB type system. Like, the droop is set to what they say it is, or the voltage control is enabled using whatever scheme they reported. That the model initializes and it runs using the required time steps that we define and the compiler that we use. Things like that. In order for a project to actually get a Q number, the model needs to be in an acceptable state in accordance with our criteria. We'll also require a report showing a benchmarking analysis between the PSCAD model and the PSC model submitted with the interconnection request. This is because we want to make sure that the PSC model is also as accurate as possible. We put a lot more faith in the PSCAD models than we do the PSC models. We believe that more emphasis is put on those PSCAD models, and so that's why we try to line up the PSC model with that PSCAD model within reason. There's limitations to it, again, because of everything I discussed earlier in the presentation. We'll also run things like playback testing to make sure that the plant rides through for PRC24 required voltage and frequency curves. Some other model-specific requirements are that it should support interpolation. It should be a full bridge representation. We don't want highly abstract approximations for the voltage source. The model should come complete with documentation, so we know how to use the model, and it should have user-accessible inputs and meters, so we can actually plot all the various responses and get all the data out of this. We do think that models that use actual hardware code work better. We haven't quite moved to requiring that yet. It's probably kind of in the works here. But in general, the model needs to include the full detailed inner loop and outer loop of the power electronics and their associated controls. So that's pretty much everything about the PSCAD models. Some lessons learned, EMT studies are just far more time intensive than traditional transient stability studies. If an organization has no experience with EMT studies at all, I would highly recommend hiring a very experienced consultant at first and learn through them. EMT is it's not something, even if you've been running stability studies your whole life, it's just not something that you can pick up and run with. It's just far too complicated. There's too many things that can go wrong. The models are just magnitudes more complex than positive sequence models. There's so many more pitfalls that can lead to misinformed decisions. And so it just really requires an experienced hand to get right. Because of the highly complex nature of EMT studies, they're also very computationally expensive. And so if an organization is going to start running EMT studies, they'll need to invest in both the highly specialized training, to run the studies and the hardware to run the studies. EMT studies can show things that have been missed in stability studies. As I mentioned earlier, they're higher fidelity models, and so things like PLL loss of sync or phase angle jumps can be captured. And so an organization will need to be prepared to make decisions based on those sort of new failure modes. Starting early and doing studies in parallel can help timelines stay on track. We found that EMT studies take the most time out of any part of the study, and with good reason, right? They're more complex. But it's a necessary component of any IBR interconnection. So to try and keep the study timelines down, we make sure that the studies are started as quickly as possible, and we try to run them in parallel. Right? We have very specific rules around which generators have to respect each other in these studies, in what order they come in. Lastly, like I mentioned earlier, investing in powerful hardware will keep the study times down as well. For some background, a small system like a single wind farm connected to a SMIB running on, say, like a generic laptop can take anywhere from seconds to minutes, but running a system with hundreds of buses and, tens of IBRs connected can't be run on a laptop with any sort of reasonable time frame, right? Even running on a very expensive desktop with 64 to 128 cores can take 3 to 4 hours per contingency. So if you have 4 different dispatches and 10 different contingencies running, you can imagine it's going to take weeks to run, even with this powerful hardware. So just keep in mind that again, investing in hardware or even cloud computing is useful. Also keep in mind the post-processing, there's going to be a lot of results that come out of an EMT study. And just a final word here, there's a lot of NERC activities that are pointing more and more towards requiring all entities to run EMT studies. And so really now is the time to start getting ready for it. Don't wait till they come out because that's going to be too late. And I think that's everything I had. Hopefully folks found this useful, and maybe some entities out there who haven't started EMT now have a better idea of what they need to do. And thank you.
Thank you, Brad. If I could get all of our speakers from today back, we have quite a few questions. We won't be able to address them all, most likely. We'll try to group them up as possible. And I actually want to kind of go back on a few things that Puyan had said directly, and I'm sure others would want to chime in here as well. And so obviously we had some nice model measurement validation from the unit specific testing to creating those aggregated models. And Ryan, of course, addressed this earlier today of this gap between the unit site IBR behavior and the models that we have. And so do you have any thoughts addressing, where do you feel like these gaps lie, and what really needs to be targeted to address that?
That's a question to me.
Yes.
Yeah. Honestly, this is just my thoughts. I think all those pieces can be done. And I showed you plots where they had been done many years ago. The gap is just understanding, having dialogue, educating, so we do it more and more often. There are cases where, unfortunately or whatever, that was neglected, and then it leads to these big event scenarios, and then we think everybody's making that mistake, and it may not necessarily be true. So it's the gap is more and more people have to come on board. That to me is the gap. I don't think we're doing rocket science here. It's not something that didn't exist. Even EMT studies have been doing it for 25 years. It's not something new.
All right. And I don't know if anybody else wants to kind of address. We're going to have a few more questions on, where this validation takes place. And maybe that's a good segue into some specific questions for you, Brad, on those EMT studies. You mentioned that model validation phase there. Just in general, provide us a little bit more information around that process with your interconnection customers. How is that model validating, going back and forth? Who has the responsibility of required parameters to get you a validated model to start your study?
So there's specifically the word validated there. That's a bit of a sticking point. We don't require specifically validation, right? Because validation is like Alex and Poyan and a few others were talking about, where they're taking the measured responses and comparing it to the model. We do require verification, right? We do require attestations from the OEMs from the developers, saying that what they are giving us the models for, right, did come from the OEM specifically, right? So our process is to really require the developers to hold that responsibility, and then what we verify with that model, we do essentially what's I think coming out as conformity assessments to make sure that that model does meet the minimum requirements for use in a study, and so we can make good, sound interconnection decisions based on the responses from that model. Because remember, at the point in which a model is produced for an interconnection request, there's no physical equipment really, right? There's an individual unit turbine or inverter but there's no actual plant. There's nothing to really validate outside of that unit level response. And so really the best you can do in that scenario is, definitely do like ERCOT does, right, where you're getting that, hardware in the loop type validation for the unit. But the rest of it is a lot of just verifying, the parameterization of that model is coming from the OEM, and it's a it's a well-established model.
One other thing, if I may, Lauren, on this whole
Absolutely.
validation piece, because again, you asked gaps. And again, this is just a thought I put on the table. And I'm human, I make mistakes too. No one is flawless. But 25 years ago, I remember in the industry where we had almost no standards. It was just like, here's a model, off we go. And now I see where we're getting more and more and more and more rules and checklists. I see a gap in just open, honest dialogue and engineering judgment, because you could check all the boxes and still there's be something that's not quite kosher if you're willing to. And I've seen that happen sometimes. You look at it and say, that just doesn't look right. And if you start questioning, and you can have an open, honest dialogue across all the parties without the fear of pointing fingers or it's your problem, it's my problem kind of thing, you can very quickly come to a conclusion and fix a problem over, say, a conference call or something, rather than letting it just be all checking boxes and off we go. So that's why I put the word moderation there at the end of my presentation. We have to be careful not to go from one extreme to another, and be always able to use our engineering judgment and our ability to truly consult together to fix these problems. And I'm not saying we're not doing that. I'm not saying, I think everyone on this call seems to be doing that, but that's kind of the gap I see, that more and more people have to be able to implement that, if that makes sense.
It does, and I think, and I'm Brad. There's a few more kind of follow-up questions around y'all's process. Around absolutely, especially if you're going to involve an EMT study and a system impact, and you spoke to the volume of work that really translates to as far as timing. But I mean, how long does that generally add to your system impact? You talked about some efficiencies of parallel, getting started early, getting models correctly. Usually, what is that adding to your system impact timing? How many engineers are typically involved? You mentioned kind of bringing in consultants and that kind of workload. And I mean, I think that's a common question under, the FERC timelines that we are trying to get these interconnection studies done upon.
Yeah, and that's a really good way to phrase it there, right? We're trying to get these studies done within the FERC mandated timelines. And so there's a give and take, right? The study needs to be as accurate as it needs to be to maintain reliability, right? But at the same time, we need to streamline and do what we can and, use our engineering judgment to make assumptions in order to move it along. And so I really like what Deepak is saying there. It's, engineering judgment is huge, right? You can't have bright lines for everything. You need to have engineering judgment. But as for the sort of workload, if everything goes smoothly, you can have it done within a few months. And again, it's being done in parallel with stability studies. And if it goes poorly, that can add a very, very substantial amount of time, because you're working, you're going back and forth with the OEM, you're going back and forth with the developer. It can add weeks to months on top of the original timeline, which is, why we see a lot of backlogs, really, is because, we'll see a problem. Folks don't always want to jump to transmission solutions. Obviously, they want to try and tune the model out of it. There are corrective periods that we have in our process. But all of that translates to time. As for the number of engineers, I actually, we do the model vetting ourselves internally, and we have, just a few engineers who are doing that part because that's pretty standardized. But as for the actual study, we do hire it out to a consultant for the bulk of the study, and so I don't actually know how many engineers at a given time they assign to it, but I do know it's more than a few.
Yeah, and of course that's also probably dependent on your overall volume queue as well.
I'm sorry, what was that?
Oh, I was just mentioning, that's also probably scales up and down based on the number of studies you have currently in the queue.
Oh yeah, absolutely. Yeah, the timing. Again, there's specific requirements around who respects who in their studies, and that can also add timelines if the previous guy's model wasn't up to snuff. So that's why you want to get it right the first time. You don't want to have to be going back to a developer saying, hey, we need to fix this in your model, because that's just going to add study time delays for the next person.
All right. We also received a few questions, I think specifically pointed at you, Deepak. EMT mode also based on admittance and current source representation of power system elements when it comes to network solution in each time set.
That's definitely true, but there is a certain nuance there, because in EMT solvers, sometimes you may not have a strict differentiation between what is a differential equation and what is a network solution, because it depends upon how the different elements are interacting with each other, especially if you have the network's dynamics also represented. But if the EMT solver does happen to do that, I think my point was that just going by the fact that something is a current source or an inverter is behaving like a current source isn't necessarily a recipe for disaster. So when we talk about future technology, when we talk about the behavior of these resources, there is a distinct difference between how we may make some assumptions to represent them in simulation domain versus what kind of behavior these inverter resources would actually provide. And we should be careful about that nuance when we talk about future inverter technology and what kind of technology we want for the future power system.
Okay, great. So I guess kind of taking it from the modeling, maybe back to more of the performance validation, and Puyan will get you back in here. Who should be responsible for disturbance monitoring and data acquisition for checking performance, validity, and modeling of the generator?
I don't know from a legal standpoint who should be responsible for it, but certainly it makes more sense to have the GO put the monitoring equipment out there, because they have the access to the plant. Now, I know there are already, I don't want to mention them because I don't want to put names up without asking them, but there are, let's say, TOs in North America who do that and work with GOs where they have monitoring at the plants, and they will get the data and they will do this kind of post-commissioning verification. And if they see an issue, they call up the GO and talk to them. That's a good model. I'm not saying everybody needs to do that same thing, but there are entities already do that. I think it's easier for the GO to install the monitoring equipment, but whether it's easier for them to then send the data to the TO to do it, I don't know. I'm not a lawyer. I'm not a politician. I'm an engineer. I don't know. Did that answer your question?
Well, and I think it's probably one of those things, much like when we talk about model verification for studies, when we're also talking about in the monitoring world, it's probably one of those two-part things. You have geo devices and TO devices, and are we all kind of seeing the same behavior?
Yeah. But I mean, that sort of equipment is pretty standard now. You can easily get a DFR that's PMU capable, time synchronized, stick it there, and remotely log in and extract the data. The legalities of who pays for what, I don't presume to want to answer.
So we did have some questions around kind of the model equivalency and then the detailed model needed under very low system strength conditions. And I think, Puyan, you kind of mentioned this a little bit as well. And so I think it was during your presentation, does that assertion that the POI looks the same as the detailed model hold under very low system strength?
Well, again, if you use the right tool, yes. So I think even in EMT, and Brad and others can comment, even when you're studying that very low short circuit scenario, you're not necessarily building the entire plant down to every piece of cable. You're still building an aggregated model, but you're doing it with very detailed equipment level models. So yes, if still all you're worried about is what's happening at the POI, I think that holds. That was in that kind of Hydro-Quebec paper, people. It's in the slides. You can go load it up and read it. It's not, it's public. It's an IEEE paper. So it goes, all this stuff goes back to what it is you're trying to do. If someone was saying, well, I'm worried about harmonic distortion inside the collector system, then yeah, of course, you got to model the collector system in every piece of cable and see if you need additional filtering, passive or active filtering in the collector system. That's a different story to, okay, I'm worried about, will the plant ride through a fault at the POI? It's a different story. Brad, do you want to comment?
Yeah, I couldn't agree with you more, and something I missed on. In EMT, right? You can do a lot of different things with EMT, but you still have to have the right model to do it, right? Not every EMT model that comes from OEM is, say, sufficient for harmonic analysis, right?
Yeah.
Or lightning strike analysis, right?
Exactly.
There's different models and there's different tools for the study. It all depends on what you're looking for.
Exactly. There's another example. Let's say you're worried about something on the mechanical side of a wind turbine. That's a different EMT model than if you're worried about electrical interactions.
Mm-hmm.
All right.
Lauren, I think we need to close out.
Yeah. As I say, we are coming up to the end of our time. Julia, I don't know if you had some closing comments here.
Yeah, I would like to thank you, Lauren, and all presenters for an excellent session. As I mentioned in the chat there, we'll address all unanswered questions and post that spreadsheet with Q&A on the event page next to the session. And so I also wanted to announce that tomorrow we have a third session, third day of this workshop where we'll talk about IEEE 2800 standard. We'll a little bit discuss in the intro about VRT requirement language that's in the NOPR and bring some background to that too. And then the last session of the workshop will be on I2X initiative that's kicked off by DOE, and then I'll close with some highlights of the workshop. So stay tuned for tomorrow and see you there. Thank you so much for attending. Bye.